In this video we're going to review some gearbox calculations, and at the end I'll take it to Matlab and show you how you can use the symbolic toolbox and the units part of that to help you figure out what kind of load a gearbox can help you lift with the project that we'll be working on this week. Okay, so here is the gearbox that I did and showed you the video about if you look on the assignment for the Arduino Gearbox Lab. This is that video where I'm lifting as much weight as I possibly can. Okay, so I say possibly can based on this gear ratio. I'm trying to lift a lot of weight. Alright, so what we had here was, if you go back to the video, we had the blue gear that was connected to the stepper motor drive. Okay, so this gear is the driver gear right here. Alright, and then it was connected to a pink gear, and the pink gear is a compound gear with the yellow gear shown here. Alright, and finally we used another pink gear and connected the shaft of that to the spool that lifts up the weight for the project. Okay, so one of the things we need to know is the torque that's possible out of the motor, and I gave you the motor specifications. So if you look on that particular file, it's got the specs, and it says on here that the friction forces that the friction torque that the motor can produce, meaning the load it can handle, is 6 to 1200. And here's a weird unit. It's gram force centimeters. Okay, so a mass times a distance is not torque. It's actually, it needs to be a force times a distance to be torque. All right, so gram force is found by looking at grams and multiplying by gravity. Okay, so that's the gravitational constant, 9.8 meters per second squared. Okay, so I'm going to show you that here in Matlab in just a second. It's a strange unit, but it's also a convenient unit for stepper motors of this size because it gives you answers that are in the range that are easy to talk about. Okay? Alright, so let's move forward with it. And what we know is, or what we're going to calculate, is the torque associated with each of these shafts, and then I'll let you go in and fill in the speed as another component of this project. Okay, so if you're looking at torque, the torque for shaft A is the same as the motor torque, okay, because it's tied to the motor. All right, so from there we can look at the gear equations, and we know that these are really not very good gears, right? They're from Teacher Geek, they're plastic, there's a lot of friction forces, there's some wobble. There's lots of things that would make this not be an efficient gear. All right, so we'll put in a parameter, an efficiency parameter, for the gear shaft that's connected at the connection point between gear A and gear B. Okay, I should say the blue gear and the first pink gear. All right, so you have this efficiency, and then you also have the gear ratio formula. All right, so this is a smaller gear going to a bigger gear, right? So from smaller to bigger, it would be less speed, right? And so the torque would go up. Speed goes down, torque goes up. All right, so that's how I would figure out that ratio. And so I know we have 50 divided by 40 as the first gear ratio, 50 and 40. All right, so that's tau B. All right, then this is a compound gear, so I know that the gear with 10 teeth, the yellow gear, has the same torque as B, okay, and it's also rotating at the same speed as the first pink gear. All right, so we can look at the torque for the shaft of gear C, and we still have an efficiency all right, the efficiency of, I call this eta A. I should probably say it's eta 1, right, because it's an efficiency based on the coupling between two gears, right? It's not associated with a single gear. They have to work together to have friction forces. Okay, so the torque associated with gear C is eta 2 times tau B, and then we use the gear ratio. Okay, again, it's a smaller gear driving the bigger gear. Okay, so that would be 50/10. All right, so we're getting a long way with that. And then we have to account for the fact that we have a spool. All right, so we have a spool, and the torque equation for the spool is that if you have a torque C, you can lift a force F, all right, times RS, that's the torque. All right, so as long as the force is not greater than that torque, we should be able to lift the weight. If it's less than that, it should be able to move like it's supposed to move. All right, so we can solve for that force, which of course in this case force is the weight of the object that we're trying to spool up. Okay, and so solving, you would get tau C over RS. All right, so I made some assumptions about the way I set up the spool. All right, the spool is actually a little smaller than 0.5 centimeters initially, but when you start winding string around it, I think on average it's about 0.5 centimeter for the radius. That's that's sort of eyeballing it. Okay, so that gives us a weight that we can lift with that particular gear ratio. And remember, that was our goal for this gearbox, was to see, what kind of forces can we get out of this with gearing it so that it'll fit in the gearbox and have as much torque as practicable. Okay, here's a different configuration of the gears that trades off torque for increased speed. So you won't have much torque at the end, so you won't be able to lift nearly as much, but it will spin much faster. Okay, so here's the idea. You have a big gear, all right, tied to the motor. All right, so that's the driving gear, gear A, and it's spinning at a certain rate. You would actually know omega A, all right? And so from there, you have a big gear, all right? So that's spinning at the same rate as the motor, and it's driving the small gear, all right? So the small gear, obviously, I think that's obvious, would spin a lot faster than the shaft of the motor, which is tied to gear A, okay? And so omega B here would be faster by a factor of the gear ratio, 50/10. And remember, we don't lose any, we have an efficiency factor for these gears, but we don't lose any speed due to the inefficiency of the gear. It's mainly, it's all in the torque. You lose torque, but you don't lose speed. And the reason it's all in the torque equation is because you have that constraint that the teeth still have to interlock. So they're gonna fit this equation for the gear ratio. Okay, so once you have omega A, you can calculate omega B. If you have omega B, you can calculate omega C, and that would give you the overall spin rate of the spool. Okay, and from there you can figure out how fast the spool is taking up strain. Okay, so then how do we work the torque? All right, so remember, we know the drive torque, all right, because the motor is tied to the shaft of the first gear. All right, so we can calculate tau A like we did in the previous parts based on the motor specifications. We don't calculate it, we look it up, plug that in. All right, and then the gear ratio shows that we're losing torque between gear A and B due to the gear ratio and also the inefficiency of the gear, just like we did in the previous part. All right, so then gear B drives gear C, and it's a similar calculation where you have a remember that's a compound gear at B. So you have a big gear driving a small gear again. All right, so because you have a big gear driving a small gear, you're losing torque. Gaining speed, losing torque. And you have an efficiency factor for that as well. All right, so you can run those calculations through and get the overall force, because the force is just the moment arm generated by the radius of the shaft. All right, so you start with tau A from the motor specifications, calculate tau B from the gear ratio and the efficiency that you're going to estimate. Then take tau B, move that down to here. You can calculate tau C. Once you have tau C, you know the radius of the shaft, you can get to the force that you'd be able to lift. Okay? You could also do these in reverse. So if you were given a certain force or a certain weight you wanted to lift, all right, you could work that backwards and find out what gear ratios would work for you. Okay, so hopefully that helps with your gearbox design. Take these ideas, run with those, and try to figure out how to lift. You got to lift at least 6 ounces, all right, in this project. So you can't go down to, I think you'll find if you use this gear ratio, all right, where you use the 50-10, 50-10, it's not going to be able to lift very much weight at all right, just a few ounces. All right, so you're going to have to change the gear ratio in order to lift more weight. Okay, so now I'm in Matlab, and I call up this symbolic units class that Matlab offers, and I start to define some parameters. Okay, so initially I put in the spool radius. I'm just guessing on efficiency. All right, so 0.7 might be optimistic. This is just a guess. Normally a spur gear like this has a pretty good efficiency, 90% or so, 95. You can Google that and find reasonable numbers for that. But these, you have to admit, these are just plastic gears with wooden shafts, really wobbly holes, lots of friction. So I'm thinking it's not going to be as good. All right. Then I get this from the data sheet. And when I look at this 600 gram force, okay, that actually has a name. Okay, I didn't know that before I did this. So if you click on that, I've forgotten what the name is. It's a pond. Okay, that's a physical unit of force. Okay, gram force is 1 pond. Didn't know that. Okay, now we do. All right, so gram force times centimeters, that gives you the rating from the data sheet. Okay, and then just to be consistent, I wouldn't have needed to do this in MATLAB. I could go straight to tau A, but this is showing that I have the blue gear connected onto shaft A is driven by the motor. Okay. So then I can ask it to report. I didn't hit a semicolon. That's the reason I reported that. So let's do that and rerun it where it looks a little better. Okay. Then the other equation I put in directly from what I had. Let's do the first one first. Okay. The first one we were trying to lift as much weight as possible. Yes. So I have that in there, right? All right. So I implemented those equations like we had. We had 50 over 40 first, and then 50 over 10 second. We take care of the taus with the efficiency. Remember, speed, you don't put efficiency in there. The speed formula is locked in because of the teeth constraint. So there's no change in speed due to gear formula. All right. I'm sorry, due to friction losses. The gear formula applies even under friction losses. All right. So then, once I have the torque at the motors at the spool, I can convert that to a force and get an idea of how much weight this can lift. All right. So I ran this, and it's showing 8
0.1 pounds, you know, if the gear efficiency is low, like maybe it's 30% efficient, you can rerun that and get an idea of a range. 1.4 pounds. Well, I was getting 5 pounds out of it. So, and I probably could have gotten a little more, but I was noticing that the gears were really starting to strain. I feel like it wouldn't be the motor that stopped, it would be a failure of the gearbox. So that's why I stopped at 5 pounds. So I'm guessing it could have gone up a little more than that. So if we said 0.6 and reran this, you get a little more than 5 pounds. So somewhere at least 60% efficient probably, all right? And we see that we're predicting that this would lift 6 pounds and have a video of it doing 5. So that seems reasonable, okay? All right, then I wanted to show you, if you just change this to grams and then multiplied by u.gn. U.gn is Matlab's version of gravitational constant, okay? So I'm multiplying grams times the gravitational constant to get gn. I'm sorry, to get gram force. Okay, so I run that and I get the same answer. So you see that's the definition of gram force, but I do find it interesting that you can just totally bypass that step and put in gram force as a unit. Matlab knows about that unit. Okay, so on our next application where we were trying to lift things as fast as possible. Remember, the motor's got a fixed speed. All right, so can we gear this up as much as possible where it'll go faster? Okay, and what I did there was I used the 10/50 for the first, for the first driven gear. The pink gear was driving the yellow gear. The gear ratio was 10/50. And then again, is a compound gear, but the yellow gear was driving, I'm sorry, the pink gear was driving the yellow gear, and it was, again, 10/50. Use the same efficiency factor and rerun this, and you see it drops down quite a bit to 0.03 pounds. All right, here's the nice thing about Matlab. It's hard for me to think in that small of a unit, so we could put ounce force, all right, and rerun that. I don't know why it's taking so long. Okay, so it's less than an ounce, 6/10 of an ounce, right? And actually, when I ran this, I could get up to about 0.75. So if I just tweak my efficiency just a little bit, let's say 0.7, rerun this, 0.82. So it's, you know, maybe a good estimate for the gear efficiency might be 0.65 based on that one data point that I had, right? Where when I loaded just a fraction more than 3/4 of an ounce onto this highly geared setup, the motor wasn't able to lift that. It would stall out. Okay, so hopefully these calculations help you as you design your project this week.